Hi, welcome to this session. My name is Danilo and I'm part of the developer relations team. And in this session, I'd like to show you some techniques that you can use to analyze data using Lambda functions at any scale. And the idea is really to cover multiple use cases and multiple techniques. So we'll start looking at an event-driven architecture that you can use to enrich your data sets. Then we will move into some more advanced use cases that are typical of data analytics, like Monte Carlo methods to use randomness to find solutions. Ensemble methods also work very well because you can use Lambda functions to run all the components of an ensemble method in parallel. And then one of the problems you might have is how can I manage the dependencies of my functions if I need many libraries. And that's where the Elastic File System can help. So we'll see how you can use EFS to host your function dependencies. And using this, we will see a few examples for machine learning inference, and also some demos of how you can use this with, for example, random forest classifications and other interesting use cases also related to Jupyter notebooks. So without further ado, let's start with the event-driven metadata extraction and enrichment. This is a very common use case when you have your data that normally is uploaded in files into an S3 bucket. And this data can be, for example, unstructured data like customer reviews, social media comments, or even videos or pictures. So how can you improve the information that you have? How can you enrich it? So you can trigger, when an object is uploaded, an enrichment Lambda function that can use any code you want to analyze this data. And one very simple way to do so is to use the fully managed machine learning services that we provide in AWS. So for example, if an image or a video is uploaded, you can use Amazon Recognition to analyze the objects that are in this image, in these videos. If you upload a text, you can use Amazon Comprehend to analyze the sentiment of the text, or you can understand what are the entities mentioned in the text. You can use Textract, Amazon Textract, to extract text from scanned documents. You can use Amazon Transcribe if you have an audio file with a conversation to transcribe that conversation into text that then you can, for example, analyze with Comprehend. Or you can translate everything into a common language. So if you have multiple languages, you can maybe translate everything to English and then analyze the English translation. Then you can write the output of this analysis as a, for example, as a JSON file with the same original name of the file into an output S3 bucket, and then you can use this as reference. If you need a fast lookup of this information, you can store them directly inside DynamoDB table. Consider that a single item in a DynamoDB table can be as big as 400 kilobytes, so it can be enough for your use case or not. If you just need to analyze the data, maybe the more optimized solution is to send this information to a Kinesis data firehose delivery stream that can buffer this and write larger files on S3 and can also maybe optimize the data format. For example, you can write the output in a columnar data format, for example, like Apache Parquet. And then you can use a tool like Amazon Athena to run SQL query and analyze the data, the dataset on S3. One of the classical methods to find solutions where you don't have an exact formula is Monte Carlo. Monte Carlo methods, as the name suggests, are based on randomness, and they can help you solve problems where there is not a perfect solution. So, for example, let's say that you want to compute the area of this cloudy shape that you see in this slide. How can you do that? Well, one way is to embed this area into another shape that you can that you are able to compute the area, like a rectangle, and then you send uniformly distributed points. So you select randomly uniformly distributed points inside this larger area, and some of these will fall inside the cloudy object. Those are hits, and some of these will fall outside, and those are misses. If you count the number of the hits and you take the ratio over the overall number of points that you draw, this is the same ratio of the two areas. So if you know the area of the rectangle, you can estimate the area of the shape inside. So this is a classical example of Monte Carlo methods, but you can use this in any way. For example, you have maybe a large customer base and you want to estimate the churn ratio, so the probability that customers are leaving. Maybe you can compute that on a single customer, but you can compute that on millions of customers because it's too complex, too heavy. You can take a sample and use Lambda functions in parallel to process this. So you can distribute this load in parallel using a serverless architecture. And Monte Carlo methods are used in lots of different fields. So in the physical science, so for example, fluid dynamics, even in the design of large-scale wireless networks. A very common use case is in finance, where they're used to estimate the risk of and the uncertainty that is affected based on the possible options that maybe some actor can take. So there are decisions, depending on this outcome, there are implications. You can simulate and emulate what can happen. And you can use 10, 100, thousands of functions in parallel to extract this random sampling, because with Monte Carlo methods you repeat this random sampling of data and then you apply statistical analysis on the result. Another category of methods is the ensemble methods, where you normally create a set, use a set of samples of iterations, and then you analyze this set. And a classic example is ensemble forecasting. The idea here is that sometimes a forecast is very depending on the initial condition. So this is classical for classic example of weather forecast. But the same applies to any other method. Maybe you have a way to estimate the churn, so the possibility of a customer leaving your platform using a machine learning inference platform, but you're not 100% sure of the input data. You don't know how sensible this machine learning inference is to input data. So if you look at the figure, instead of having a single input and then you apply your forecast to get an output, a result, you can take multiple inputs close to the initial conditions, so you slightly change the initial conditions of your customer, and then you apply your inference, your forecast methods to get different outputs, and then you see how these outputs are affected. So the idea is really something that works well with Lambda function, because you can run 10, 100, again, thousands of Lambda functions that can compute different scenarios, and then you can get the final result, the final forecast. In weather forecast, this is very common. So, for example, if you run 100 weather forecast scenarios with all they are uniformly distributed across your input values, then if 56 of these simulation expect rain, then you can say that you have a 56% chance of getting rain. Another technique that works very well with Lambda function is ensemble learning. And the idea here is that instead of using a single machine learning algorithm to build your prediction, you can get better performance if you use multiple algorithms in parallel, and then you find a way to get an ensemble result. And in doing so, you can use also simpler machine learning models, and the fact that you use them together gives a better result. So let's say that you have a data set. So instead of training a single machine learning model, again, it can be the machine learning model predicting the churn probability of your customers. Instead of using a single model, you can use multiple models with different hyperparameters, or you can use different algorithms as well. So maybe you can use a linear learner, a logistic regression, you can use XGBoost, and so on. And let's say that you create 5 models, then you can take the prediction, the inference from all the models. For example, let's say that you are doing binary classification, so you get a 0 or a 1. In this case, you get 4 zeros and only one model is returning a 1. You should define a way to build the ensemble prediction. So in case of a finite number of results, you can, for example, set up a majority model. So in this case, you can say the majority is the 0, so the result is the 0, or you can use more advanced techniques. You can take the mean, and the result in this case would be 0.2. That brings more meaning forward. To do this kind of analysis, normally you need libraries that simplifies the manipulation of numbers, of vectors, of matrices, and the most common platform to use is Python. So for Python, we provide an AWS managed layer that includes NumPy and SciPy, that are the 2 foundational modules that you use in any data science stack. And that's a quick way to start using Lambda functions with this layer and do some data analytics. Actually, often you need many more layers, and this can go beyond what you can include in a zip file. So one way to overcome that is to use the integration with the Amazon Elastic File System to host in the Elastic File System in EFS the dependencies that you need. So what you can do, for example, is extend the reach of Lambda to completely new use cases using machine learning frameworks, for example. So you can do machine learning training. You're using a CPU-based environment, so you have 15 minutes of time limit, but this can work very well, for example, with Ensemble learning, where you are training multiple relatively simple machine learning models in different Lambda functions, and then you can combine the result of the models when you do the prediction. A very common use case is machine learning inference, and we see a few examples of that. Again, you're using CPUs, so the latency can be higher than if you do inference on GPUs. But depending on your latency requirements, this can be okay. So in the event-driven architecture that we've seen before, since everything is asynchronous, so if you wait for 3 seconds or 20 seconds to get a result, maybe it's not really changing a lot for you, so it can be okay. And if you need a fast response, then you can use provision concurrency and move everything that you can in the initialization of the function. In this way, you can avoid cold starts and you can have a faster inference. To populate the EFS file system with your dependencies, you can use an EC2 instance and install your dependencies and then mount this file system in your Lambda function. There are also some tools created by the AWS community, like this tool created by AWS hero Michael Hart. And this is an example of what you can do with machine learning inference with EFS. This is taken from the blog post that I wrote when we launched the integration of EFS with Lambda. It's using PyTorch and a fully trained model that is available in the PyTorch hub. It's downloading the model on the first invocation on the EFS file system, and then it's persisted there for the next invocation and even for the next cold starts. And it's doing bird classification from images. So you pass in input the link to a URL, it's downloading the image, and then applying the model. My friends and colleagues Giuseppe and Diego created this blog post where they're using, in a similar way, TensorFlow to do object classification inside an image. And again, EFS is hosting the dependencies. And more recently, my friend and colleague Eitan, this blog post where he's using XGBoost, and again, he's using an EC2 instance to train the model in this case, and then deploy the model and the dependencies on EFS so that you can use them to run inference in a Lambda function. If you want to create your own data science dependencies on EFS, so since we're using Python, you start by defining your requirements in a requirements file, and this is the list that I'm using today. Then you can mount an EFS file system with an EC2 instance. You can change the permission so that you can write into this directory, and then you install Python 3.8, the same version we're using with Lambda now. And then with pip, you can install this dependency straight into the EFS mount point. Now you can create an EFS access point, that is what Lambda is using to mount a file system. Basically, it's telling, mount this file system with this user ID and this group ID. In this case, I'm using EC2 user, is the standard user for Amazon Linux. You connect the function to the same VPC as the EFS file system. Be careful if you need internet access or access to other AWS services. You may need to create a NAT gateway, or for services like S3 or DynamoDB, you can create and use a VPC endpoint. And then you can add the file system to your function. And last point is that every runtime environment normally has an environment variable that tells to the runtime where the dependencies are. So for Python, you should set the Python path to the directory in the mount point used by the EFS file system to find the dependencies. So let's now see a demo of what you can do with EFS, and we will cover a few use cases. In each use case, I will use a single Lambda function executed at a time, but think that you can use this in parallel, for example, with techniques like Ensemble learning to train multiple machine learning models and then use a predictor that is combining the results from all these different models. So let's start with something that is very common, so a random forest classification. So with random forest classification, we want to classify some data points. So in this case, I have 2 samples that I use for training. Each sample has 3 features, 3 numbers, 1, 2, 3, and 11, 12, 13. And I want the first sample to be classified as a 0, and the second sample to be classified as a 1. I fit the classifier with this very simple data set. Then I create another variable with a list A with a list of other samples, and I can get the prediction. And then I can format this prediction in the same format that the API gateway expects when returning a result. In the Lambda console, these are the functions that we're using today. And this is the random forest classifier function, same code that we saw before. I'm setting the Python path to the path used by the EFS file system so that all the dependencies are found. And if I go into the alias, I can see the configuration of the API gateway and the API endpoint, so the endpoint that I can invoke. To invoke the API, I'm using Postman, a tool that provides a nice interface, and I can see the result very easily. So let's format this as a JSON, and you see that I get a prediction on the initial data points, the one that I use for training as 0 and 1 as expected, and on the new data points I get a 0 for the small low numbers and a 1 for the high numbers. So this is a very simple model, but it works, it's been trained, and I can use it inside a Lambda function. Let's now run a logistic regression inside a Lambda function. So to do so, I start by creating a pipeline with multiple stages, 2 stages here. The first stage is a standard scalar that formats all numbers in a standard range. Then I use logistic regression, one of the most common predictors that are used. Then I download the iris dataset. This is a dataset of a picture of iris flowers classified with the different subspecies. And then I split the dataset in train and test. And then I use the training dataset to fit the model. And then the Lambda handler is using the accuracy, computing the accuracy score of this trained predictor on the test dataset. And again, the accuracy score is formatted for the API gateway. So let's go back to Postman, and let's see the result, and we see the accuracy score is very high, it's almost 1, so, but this is a very well studied data set, so it's very easy to get very high results here. Sometimes you want to return an image from an API, and in data science you often generate images with a tool like matplotlib that is generating a graph or a visualization from your data. So when you have an image, what you can do, you can store the image into a bytes.io object in Python, and then you can use the AWS SDK for Python, Boto3, to upload this image to an S3 bucket. I use a public read ACL here, so it's publicly readable. And then I create the public URL of the object, and I return that with the API gateway with an HTTP return status that is 302, so it's a redirect that the client will follow and will follow the redirect to the image. So let's use this with Postman. It takes a little bit of time to create the image, and then Postman will follow the redirect, and this is the image. So this is an example of anomaly detection. Each row has the same data set, and in the columns we have different algorithms. The anomalies are flagged in orange, and some algorithms also return a black boundary around the anomaly. And you can see how the different algorithms are finding and working with on the same data set with different results. And at the end, we also try to give a completely random data set that, of course, by definition, doesn't have an anomaly, so the algorithms return a quite random result as well. Finally, I'd like to show you how you can use Papermill within a Lambda function. And the idea is that most of the interactive exploration and analytics is often done in Jupyter notebooks by maybe a data scientist. But then you want to execute these notebooks. You can flag some cells of these notebooks as parameters. And then when these cells are flagged as parameters, you can pass the parameters and the notebook to Papermill for a batch execution. And there are many use cases, so you can create a periodic report, depending on date and time, you can use different parameters. You can run a notebook, and then based on the result, take an automated action. or you can run a notebook as part of a larger workflow and contribute to the workflow with the result of the notebook. To learn more, these are the links of the documentation and the repo of the Papermill project. So what I want to build now is an event-driven architecture where you upload a Jupyter notebook with some cells flagged as parameters to S3, and when you do the upload, you can add some S3 metadata, and the S3 metadata can contain the value of the parameters that will be applied by Papermill. You have to be careful because the metadata size, the maximum size is 2 kilobytes, so if you need more space, you can use a different technique. For example, you can create another object with a similar name and different extension containing the value of the parameters. This upload will fire the execution of a Lambda function that will read the notebook and the parameter, will execute the notebook using Papermill, and then will write the output into an S3 bucket. To use Papermill with Lambda and S3 is very easy, similar to what we did before, but in this case you need to set in the path also Python, because what happens is that Python is the runtime of Lambda, is executing Papermill and Jupyter, but Jupyter will start a new kernel with a new Python interpreter inside the Lambda function environment. That's why you need to add this path. Then S3 is natively integrated with Papermill, so you can format the input and the output on S3 using the S3 URL. Then you can execute the notebook passing the parameters that you read from the S3 metadata. So let's see this bucket. So this is my input bucket and it's empty. This is my output bucket and only contains the image that we created in the demo before. And this is the Jupyter notebook that I want to use. It's using k-means clustering with a classical dataset of handwritten digital data. And as you can see, I can use tags in this notebook. And I have here 1800 samples, but I'm only using 300 because of the sample size. I flag this cell as a parameter, so now I can set the sample size to a different values and then execute the notebook using Papermill. So I upload the file, I pass the metadata with a sample size of 1000. Now the file is uploaded with the metadata on S3. I can check the input bucket, and as you can see, it's there. And in the output bucket, if I reload, I can see that there is also the output with the result of the notebook. So we saw many different use cases, and the idea here is really that you can run lots of logic inside a Lambda function, and then you can use techniques like Monte Carlo or Ensemble methods to leverage the execution in parallel of multiple Lambda functions. What I suggest is think if an event-driven architecture can be used to enrich the data that you have, extract more metadata, index the data in the metadata that you have. For more advanced use cases, think of using EFS to go beyond the limit of the zip file. So you can use tools like scikit, learn, or your matplotlib to generate images, and you can see the code that I will share how to do so. Machine learning inference is a very common use case because sometimes you want to have the flexibility of a serverless architecture that scales up and down depending on your need. So look at those examples that are shared to use frameworks like PyTorch, TensorFlow, or use XGBoost to run inference inside a Lambda function. Try to start with asynchronous invocations where you are not really focused on the speed of the functions, and then you can eventually refine. And finally, if you use notebooks to define your analytics, you can then execute them as a batch as part of a workflow using Papermill, and you can run that inside a Lambda function. That's a very interesting use case. So that's all I have to share now. You can find all the source code of these functions in this repo, and please give me your feedback on Twitter, and I hope you will enjoy other session for this event, and don't forget to complete the session survey. Thank you.